since then. Her main research interest is in the area of development of electrode materials for energy and environment applications. She is involved in the development of green techniques for the synthesis of nanocomposites and studying their applications in energy devices like fuel cells, battery, and supercapacitors. She is also actively involved in the development of energy efficient water purification techniques like capacitive water desalination and photothermal materials for solar steam generation. She has more than 55 international journal publications with H index of 20 and total citations of 1,300. She has also 5 patents to her credit and 2 book chapters. She has received several awards, which includes C. Bhimura Best Assistant Professor Award 2020, Mukherjee Innovation Award 2017, BRNS Young Scientist Research Award 2000. Bill and Melinda Gates Foundation 2014 and DST Young Science Award 2013. She has completed several projects from DST, SERB, and BRNS. She has guided 7 PhD students and 7 MTech students so far. So I cordially invite Dr. Neetu Jha to take over the session. Over to you, ma'am. Thank you.
Thank you, Tanaka. And I think I should thank the organizers for inviting me to this FDP. So, yeah, I think I'll just start sharing my screen. Thank you for nice introduction. And in case you have any one of you have any doubt, you can stop me in between, anywhere you can stop me. So you don't have to wait till end of the session because the session is for 2 hours, and I think let us try to learn from each other. So let us try that it is more interactive and interactive session where we both can enrich each other. So we all. So shall I go ahead, Betty and Kanika?
Neetu, you please keep a check on the chat box because everyone is muted by the administrator.
Oh, okay.
So in their own will, they cannot start talking. So if participants, if any of you have any doubts, please write in the chat box. Ma'am will look into the question and ma'am will tell the administrator to unmute that particular person. Otherwise, it will be a huge confusion. Okay? Am I clear, Neetu?
Yeah, somebody wrote that my voice is not clear. So just give me one moment. I will change the setting and hope it becomes clear.
It was audible for us.
Madam, your voice is very clear. You please continue. Your voice is clear.
Is it? Acha, is it clear now?
Yeah.
Okay. No, because one of the participants wrote in the chat box that it's not clear, so I thought maybe it's not clear. So, yeah, the topic on which I'm going to talk today is nanomaterials for energy and environmental application. And I can go ahead, right? No problem.
Ma'am, full screen. That your slide sharing screen.
Right. Yeah. Now, shall I go ahead?
Yes.
Thank you. Yeah, so whenever we talk about nanomaterials, it is an umbrella subject actually, because it's not just that environment and energy sector comes into it, but a lot of the different fields that they are a part of nanomaterials. Sorry, somebody is...
Mute everyone. Darpanji, mute everyone, including me.
Thank you. So, yeah, nanomaterials is really an umbrella subject where everything starting from biology, drug delivery, textile, and energy, environment, obviously, and all different fields are coming into it. So, we all are interested in different types of material, where nanomaterial is a type, which is very interesting, and that's why we all are studying it, right? So this is outline of my talk, where I will be talking. I will start by different synthesizing techniques, then different properties, their applications, and then focus on energy and environmental applications, including by the end I will also introduce some applications where it is being used in textile and then in commercial applications. So yeah, so I will start. So since the time immemorial, like since the time we remember, human beings are always interested in different types of material. And earlier, many millions of years ago, human being could find out that, yeah, stone is stronger than human hand. So stone can break, which human hand cannot. So they started using stones to make weapons, to use it for different applications wherever they wanted some kind of material for hunting and all. So yeah, that civilization is known as Stone Age. Now, similarly, different civilizations are named based on the materials which they mainly use, like Bronze Age, Stone Age, then Iron Age. And so we can assume that in future also, the way nanotechnology is moving ahead, the advances it is making, the new era, this civilization will be called Nano Age, or probably it can also be called Nanotechnology Age, because technology is also getting equally, technology is equally important. Material is, yes, material, and the science which we are developing it. So maybe we can call this age as Nano Age. So it is because we all are studying the materials which are of very small size, nano size. And with this chart, you might have seen this chart at many places. We have this atoms which are approximately in the range of 0.2 to 0.4 nanometer, but they are much smaller than the nanomaterial which we are talking about. And then we have small ants and dust mites. They are in the range of few micrometers. So nanometers is something which is yes, which is very small. It is a Greek word actually. Nano in Greek, it means dwarf, and it is generally one. I just will check the chat box once. Okay, so nano means dwarf, and it is actually 1/1000th of a unit. So it is very, very small. And for a quick reference, we can say that what a nanomaterial is, if it is 1/1000th of the human hair. So we all have human hair on our head. We can touch and imagine how thin it is, and then something which is 1/1000th time of that. So that means really something which we cannot see with our eyes, which we cannot touch and feel with our hands. So that small particle, very, very small. So yeah, so these nanomaterials, they are available since a long time. And if we want to define a nanomaterial, so if any one dimension of a material is in nanometer range, is in the range of 1 to 100 nanometer, we call that nanomaterial. And also, if we have aggregates of particle where agglomeration is there, if 50% of or more of the particles are in the number size distribution, so and if more than 50% of the particles are in the range of 1 to 100 nanometer, it will come in the category of nanomaterial. So it became, now this definition has been picked up from NASA, and this became very important to discuss this definition, because we cannot call something of 1000 nanometer as nanomaterial, right? So you have to define it. So any one dimension, not necessarily all the dimensions, but any one dimension in the range of 1 to 100 nanometer, we can call it nanomaterial. And if it is in aggregate, yeah, more than 50%. So nanomaterials are present since long time, but because we need these tools like electron microscope to see these very small nanomaterials, it became clear that we are using nanomaterials or nanotechnology only after the development or discovery of electron microscope. So obviously we cannot see with the eyes. You can see with eyes few meters to few centimeters, 100 micrometers is the thing which we can see with the eyes. Then comes light microscope, which helps us in magnifying very small objects like few micrometers. But when it comes in the range of nano size, we need electron microscope. And the discovery of electron microscope helped us in doing a lot of stuff which which we are going to discuss, and which we are using, appreciating, and trying to understand more and more. So this is another classification of nanomaterial, which comes under natural nanomaterial, because it does exist in nature. We are not creating it. We have not created it. Then incidental nanomaterials, which are being created by human being but unintended. So like diesel exhaust, coal combustion, welding fumes, they do form nanoparticles of very small size, mostly spherical carbon nanoparticles, which is diesel exhaust. And then engineering nanoparticles is something which we are trying to create, which are trying to make and use it and study it. So yeah, now this is something which I want to discuss. My topic is nanomaterials for energy and environmental application. But before that, we all want to know why nanomaterials are used in these applications, not just energy and environment. Of course, they are used there, but there are many other fields. Why are they used? Why nanomaterials is so important? Does it happen that you take any material and reduce the size and then you can use it, it becomes attractive? No, it doesn't happen like that. Nanomaterials are so attractive because the properties are very, very different than the bulk. And all of this we will see in this session. So it was existing since a long time, and it's just that we were not aware. It was not understood that this phenomena which we observe is because of this nanotechnology, because of the very small gold or silver nanoparticles which are present. So the recipe was available, but understanding was not there. So now, as we are understanding, we call it history of nanotechnology. So this Lacargus cup is something which is available since a long time. It's very interesting. It appears green in reflected light. If you keep it somewhere and the light source is just outside, it appears green in color. But if light source is inside and you are observing the transmitted light, then it appears red in color. So this is the speciality of Lacargus cup. It is there in British Museum in London. This dichromic effect which we observe in these cups is because of the gold or silver nanoparticles dispersed in this glass material, and this is giving it their special property. So see, gold and silver nanoparticle, as a normal person, we know today gold is yellow in color. It is silver is white, not white actually, silverish color I should say. But then when you take a sheet of gold and start chopping it. Let us assume that we take 1 centimeter to 1 centimeter size of the gold sheet, and we start make 100 small pieces. Still it will appear green. But if you reduce the size to very small size, then the color is different. It's no more yellow, and material property changes in such a way that something like gold, which is conducting in nature, it becomes non-conducting. It is noble metal, that's why we use it, right? And as a bulk, it is noble metal. It doesn't react with anything so easily. But when we go to nanoscale, it is very reactive. It acts as a catalyst. You can use gold nanoparticles as a catalyst. It shows magnetism. And so these properties are changing. We cannot expect these properties. If you just imagine that if we are not at all aware of nanotechnology, then according to us, you can never imagine that we have a distinction, like gold comes in the category of noble metal, where it does not react, and that's why it's so precious, right? But in nanoscale, no, it doesn't happen like that. It has different colors, different properties, and Yeah, so so another area where it was existing was in churches. So we might have seen the tinted glasses, and beautiful paintings with these tinted glasses does exist in churches. The reason, the why the colors is because of these gold nanoparticles. Now, gold nanoparticles, they can have orange, blue, red, green, different colors if it is available in different size and shape. Similarly, silver, it appears in different color, and the color depends on different size and shape. So it was known that for how long you will do the whatever work you are doing to reduce the size, so that you get that color, and after you get that color, they used it for making the these stained glasses and used it. Now, as I said, these gold nanoparticles, they also have catalytic activity, where the impurities, organic impurities, which come from the furniture or which are available in the atmosphere, it converts that into less harmful chemicals. So that is another reason why such glasses were used in churches. If we sit in any such place, then you can feel that the aura is different, right? We feel good. And even if the church is in highly populated, and in that the location where a lot of cars and vehicles are there, still the atmosphere inside the church is very cool, calm, and awesome, is because of these particles, which are reducing the pollutants in the air, and also the ambience is good. So yes, nanomaterials were useful at that time also. They are useful today also. And one chat says I'm missing all the information. So and continuously getting error message. So if somebody can look into it, because I don't know how to solve this problem. Okay. I'm moving ahead with the presentation, and if somebody can help, then I think Sujata Rani. So she needs help in getting access, or probably in like in this to join the meeting. So yeah, apart from these applications, some other application of nanomaterial is in the Maccas Blade. So this blade, or the sword, it was known as one of the sword which was very sharp, very strong, and yet flexible. And it has the connection with the India, because the wood steel which was exported and used in making this Maccas Blade was from India, especially from Tamil Nadu. And this sword is very, very strong sword. So recently, when they did HR high resolution transmission electron microscopy of this, they found that carbon nano tubes were present in this steel. So the steel, mainly it was manufactured from iron and carbon, and the carbon was in the form of carbon nanotube, which gave it so much of strength and flexibility. So and in India also, like the bhasm, which in India, and Ayurvedic medicines, which people are using, there are a lot of nanomaterials which are present, which are in kajal, for example, we have these nanoparticles which are present, and all these things, they help in they help in one way or the other. But the existence is there since a very, very long time. Now this is something where this was the time, which was 1959, when Feinman, he gave a lecture, and he spoke about the possibility of doing things at nanoscale, where he discussed how nanomaterials can be used, how nanoparticles, how we can convert everything into miniaturized form and do study at nanoscale. So the topic of his talk was, there's plenty of room at the bottom. And this talk was something which kind of ignited the flame to do research in nanomaterials, where the people started understanding that yes, it is possible when we can do things at nanoscale, at small scale, and we can do really wonders. Why do we need to have all big stuff where we don't need? So, and not only in his lecture he also gave some idea how we can do it. So it was in mid of this century, in 1959, when this thing just clicked him and other scientists in the meeting. So now after this, people started talking in this area, discussing in this area, and in 1974, Taniguchi was the first person who introduced the word nanotechnology. He was talking about semiconductor thin films, iron ball milling, and he spoke about how the features can be controlled at nanoscale. So Feynman spoke about things of very small dimension, of very small size, and Taniguchi gave the term nanotechnology. So after approximately 15 years of Feynman's talk. Now, after this, Eric Drexler, he was another visionary person. He discussed about how the he discussed in his book, actually, which was published in 1986, and how nanotechnology will be able to help all the different branches of science. So he spoke about robotics, he spoke about the how chemistry will help in making the machines which are of very small size, nano size, and which will be useful in many different fields and many different areas of science and engineering, which will develop objects, products, and which will be very, very useful. So his idea was given in 1986, but it was very, very useful. And he was obviously inspired by Feynman's talk. And after this, till now, we knew that, okay, something nanomaterials will come into picture, we can use it, but how to do it? Unless we see, we can't do anything. So Binning and Rohr, they made a scanning tunneling microscope in 1981, where and this machine is still being used in many labs. It is there. STM is scanning tunneling microscope, where using the tunneling of electron from one metal to the other, we can actually use this principle to see nanoparticles. To basically, the resolution of STM is very high, and we can manipulate the atomic positions and see where they are located. So now, with the discovery of STM, it was possible to see nanoparticles, to see something which is so small in size. And before this, it was always thought that it's not at all possible to see such thing. So yes, this invention was something very great and helped in accelerating the advancements which are taking place in the field of nanotechnology. So after this, in 85, Fullerene was discovered in Rice University, and they were doing mass spectroscopy of this molecular beam experiment, and then they using the graphite electrode, and they found that they are able to collect molecules which are of the size exactly 60 carbon atoms or 70 carbon atoms, which form Fullerene. So Fullerene, you have, if it is C60, then you have 20 hexagons and 12 pentagons. They give the shape, give shape of a football to the Fullerene. So it was discovered and later studied. The properties of Fullerene were studied. Then then AFM, after 6 years of the discovery of STM, AFM came into picture. AFM is again very important because STM, as I said, tunneling of electron takes place. In AFM, the laser beam is deflected, so it is it can be used for the materials which are non-conducting in nature. So both STM and AFM, they are very useful in examining, in studying the depth, in-depth study of nanomaterial. So I'm sorry for this graph, this PPT, not graph PPT, but because this is, I know it's difficult to read, but my aim here is not to make the audience read what is written on the slide, but I just want to show you how the nanoparticles, nanomaterials or nanotechnology developed over the period of 1 century. We know, we talk about nanoparticles since last 4-5 decades probably, but the material is existing since a long time before like BC, before Christ, and then Feynman's lecture 1959, then 1974 we have the term nanotechnology, then then the book by Eric Drexler, and then obviously STM came into picture, AFM came into picture, Fullerene, then 91 carbon nanotubes were discovered, and then the whole area of nanotechnology. But yes, Fullerene and carbon are special type of nanoparticles. Now then graphene, in 2001 the graphene was discovered. So and I think they got Nobel Prize for that in 2005. So these are special type of nanoparticles, but it's not that they are only nanotechnology. No, they are, you can form any material which is available. We can play around at the nanoscale. We can do engineering at that level and change the property of a material so that it becomes useful for the application we want to use. So yeah, why the nanomaterials, they have different properties, unique properties, which are very attractive, and this is what makes it so useful. So yes, I think I'll just, the imperfections or defects are less, then the classical laws, classical mechanics laws are not valid whenever we talk about nanomaterials. Mostly quantum mechanics comes into picture, which are valid, and electromagnetic forces are very strong, gravitational force is negligible. They have very high surface to volume ratio, so the surface area increases multiple times when we are using a material of such a small dimension. And random motion plays a very important role. So these are the reasons behind the property change. But how the property changes? Almost all the properties which I have listed here, like structural property, thermal, mechanical, chemical, optical, magnetic, electronic, all these property changes. So as I said, something which is conducting in nature, it becomes insulator at nanoscale. Something which is not very strong, it becomes mechanically very strong when you go to nanoscale. So some of the properties are most of the property changes. Some of the properties change in the range of microscale, and some at the when you go to nanoscale. But when you go to nanoscale, yeah, property changes hugely. Like and this is what makes them interesting, right? Because unless the property change is something, it goes like unexpected. You could not cannot expect what the property of the material will be when you go to nanoscale, and then you study it, try to understand it, why it is happening, what is happening actually, and then we use it in the applications. So we can also nowadays modify, change, functionalize the material, and manipulate the properties and use it for the application where we want to use. So yeah, when we talk about these properties, then size dependent effects are obviously seen, and these size dependent defects can be classified in smoothly scalable ones and quantum effects. So smoothly scalable properties are those properties which are related to fraction of atoms at the surface, and they, when you go to small size from big size, then smoothly they don't change abruptly. Whereas quantum effect is something where the property changes abruptly. So it depends on, like, if one shell is complete, this is the property. You complete another shell, the property will change. So that is quantum effect. Now we will discuss about these effects. Like surface property is something which is related, which is smoothly scalable property, and we see that as the particle size is reducing, the percentage of atoms on the surface is going up. So the last one, the right hand side, let's see if I can. Yeah, so this one, it has 12 atoms, and if you have something of very small number of atoms, then out of these 12 atoms, 9 are at the surface. So 75% of atoms are at the surface. And when we increase the size of the particles, then the percentage of atoms which are at the surface is less. So that is why we say that when we go to smaller and smaller size, the percentage of atoms at the surface is much higher. And so yeah, so there is something called magic number. Magic number is the number of atoms which make these clusters a stable cluster, exceptional stable cluster. So for example, if you take anything like aluminum, so let's say 13 atoms or 66 atoms make them a stable cluster. 66 atom is making it a stable cluster, but not 67 or 68. So 66 is the magic number. So yeah, and then as we if you take a look at these graph, as the cluster size is increasing, obviously total number of atoms are growing up, but surface atoms are reducing. So if with the increase in size, whereas for smaller size particles, surface atoms become very important. And this property, where this property is called dispersion. Dispersion is a parameter which you can measure for the particles, and they are fraction of atoms at the surface. It scales with surface area divided by volume. So for mostly spherical particles, you can say that dispersion is inversely proportional to radius of the particle and cube root of total number of atoms, which is making the crystal, or which is making the stable nanoparticle. And dispersion, if you plot with 1/3, then this is how it varies. It's very high for small particle, very low for big particle. Now, why so much of importance is given to surface area for dispersion is because surface area is very, very important when we talk when we are talking about the applications of yes, in energy and environmental application, as well as in other applications. Surface area is very important while you choose one application and we try to use it. So we know that mean coordination number is something, the number of neighboring, it defines the number of neighboring atoms. So if an atom is in the bulk, it has more coordination number because more number of atoms are at the neighbor of this atom. But when we go to the surface and then try to see number of atoms it has, then it is less. So in this case, x-axis, if you go towards right side, then the smaller, let me check if I can write. No, I cannot. So basically this is small size particles, nano size particle, and this one is bulk. So when we go towards bulk, and if we try to extrapolate, then this is the value for bulk coordination number. This is an example for magnesium atom. And similarly, if we take a look at the cohesive energy, that is bond per atom. Now, as the surface percentage of surface atom is high, and these atoms, they have less coordination bond and more free bonds. So the cohesive energy is also for nano size particle, it's less, whereas for bulk particles, it's more. So here you will get the value closer to 1.39 electron volt, whereas the theoretical value is close to 1.5 something. So yeah, all those things, the stability of the structure of any structure depends on the dispersion. And this dispersion, which is the fraction of atoms at the surface, it is very important, starting from the property variation to the application. So whenever we talk about these things, about the particles, you can make nanoparticle of any shape, right? Nowadays, nano flower, bamboo shape, onion shape, you will, if you go to the literature, you will find many shapes which are there in the people are preparing in the lab. So, but when you talk about any shape, the stability of nanoparticle is equally important. So if we take a cube, always corner atoms are least stable. So these atoms, they are least stable, and so they are easy to remove. Not just they are easy to remove, but if you put or if you just install this type of nanoparticle in some atmosphere, they are the ones which are least stable. So they absorb more from the atmosphere. So this atom is least stable, followed by the edge atoms here, this followed by the surface atoms here, and then the interior atoms in the bulk. So corner atoms are least stable, then edge atoms, then in plane surface atoms, and the interior atoms. So now see, if we try to make a nanoparticle, you will see that making spherical nanoparticle is the easiest one. Why? Because if you try to make this type of nanoparticle, high chances that this atom will go off in the solution because it is least stable. So yeah, and it all depends on the coordination number and the coordination number and cohesive energy of the particles. So yes, surface is important, and because of this, you have these dispersion and surface atoms. They have effect on many different properties, including melting point variations. So this is an example where where we try to see how the melting point of nanoparticle changes. So thermal so the thermal property of particle, how it changes with size. So if this is the melting point of bulk material, when actually I'm not talking about the particular material here, because this trend is mostly true for all the nanoparticles, mostly 99%. But again, you might see some exceptions also. So for most of the nanoparticle, if that is for bulk and you keep on reducing the size, after some time you will see that there is huge reduction in the melting point. And so the melting point reduces with the size. Smaller is the particle, smaller is the size of the particle, you will see that the melting point is less. And you can imagine that it is happening because this percentage of atoms which are on the surface is very high, and when you increase the temperature, vibration of atoms, they kind of start melting the material. And so yeah, dispersion is something which is very important in changing the thermal property of the material. Yeah, so this is about the free particles, when nanoparticles which are free. But now if you have a nanoparticle which is embedded in system, so let us go here first. Yeah, so that was about the free particle, and this is about the embedded system. So that means if you have a matrix and you have nanoparticles embedded in them. Now this kind of nanoparticles, they show totally opposite behavior than the free nanoparticles. Free nanoparticles are something which is free nanoparticles are they are they have reduced melting point, so they start melting at low temperature, whereas these are embedded system. Because of the pressure which this matrix is applying on the nanoparticles, their melting point is higher than the free nanoparticles. This one is for the bulk. So this type of nanoparticles show higher melting point than that of the free nanoparticle. And not just that, you do not get sharp melting point. I just need 2-3 minutes break because my laptop might get discharged and I need to put it on charging. Just give me 2 minutes. Yeah, I'm sorry for that. Okay. So for the bulk materials, we mostly see that the melting point is very sharp. We talk about 1336 Kelvin is the melting point of gold. So we can really talk about the exact numbers. But when we talk about the melting point of nanomaterial, then this is not very sharp. So if we take a look at this graph, this is for the bulk, which is at 430, but the nano size particle, so 101, then this is 34, 12.8 and 5.6. You see that this one is still sharp comparatively, but this is broad, this is broader, and this is really, really broad. Why is it happening? Again, because melting is cooperative phenomena, and which is not well defined for small number of members in a crystal. So sharp melting point is that is actually you melting point when we talk about nanoparticle, more surface atoms, so the vibration, the energy with which the atoms are vibrating to start melting it is different than the bulk atoms and then the and the surface atoms. So it is important that we understand that it is a average value which we are talking about. And when we talk about the bulk element, then there are large number of atoms which are involved. So the vibrational energy acquired by them is almost same, but whereas in this case nanoparticle, large fraction of atoms which are at the surface which are behaving differently than that of bulk, and that's why we see this discrepancy. That's why the melting point is not very sharp. So yeah, embedded system, and these are the instruments with which you can measure the melting point. So transmission electron microscope, here we have electron beam. So if this is the nanoparticle, electron beam falls on it, and then it absorbs, the nanoparticle absorbs energy from the electron beam, and by analyzing the diffraction pattern, we try to see what is the structure of this particle. But if it starts melting, the diffraction pattern changes, and exactly you can find out how, when the diffraction pattern is changing and when the element is starts melting. That is one way by which you can analyze it. Another one is a nanocalorimeter. Here the principle is exactly same as that of the normal calorimeter. It's just that we change some calculations and incorporate the contribution of the smaller size in the overall calculations. The requirement here is like narrow size distribution should be there. Otherwise, because we are not able to see the particle in TEM, at least we see the particle, so we know what is size of the particle we are trying to analyze. But in this case, we are not able to see this. So narrow particle size distribution helps in better understanding of the size, and and we also understand the correlation between size and melting point. So that is something. Another very interesting thing is lattice constant. Now, lattice constant is something which we all have been studying since our school time, and we know what is this lattice constant. So, but we have always discussed it in the form of a constant, right? We always know that it's a constant. Yet no more a constant when we go to material of nanoscale, because again, we have surface atoms, these red ones, and then we have these bulk atoms which are in the center, interior of the atoms. And these atoms are less stable compared to the blue ones. And the blue atoms, they kind of try to pull these atoms towards the interior. If it happens, then obviously the surface atoms are the distance, the lattice constant reduces when you go to small size, because these atoms are pulled to inwards. So yeah, this is something which I find very, very interesting, because lattice constant is known as a constant, but no more a constant when we go to small size or nano size. So yeah, this is another, see, I'm trying to put some effort on properties also, because these properties are something which is making nanomaterials so interesting, right? That is why I'm putting some effort in explaining these properties also. So when we say that gold nanoparticle is not yellow when they are in gold, copper is not in that color, whatever it is, when we go to the smaller size. So when these metals, they change the color, and that is because of their optical properties. So the optical properties of material changes because of the two phenomena, surface plasmon resonance and quantum size effect. This is more pronounced in metallic nanoparticles, and this one is more pronounced in semiconductor nanoparticles. Now, the color of the particles, they change when they go to smaller size because of these two effects. So what is surface plasmon resonance? We know, as I said, you see, this effect is more pronounced in case of metallic nanoparticles. We know that metallic nanoparticles, they have a lot of free electrons, and it is optical phenomena. So whenever these materials, these kind of materials with a lot of free electrons, they interact with electromagnetic radiation, where you have electric field along with a magnetic field in perpendicular direction. This electric field interacts with this free electron, and they apply a force on it. Due to that, the electrons of the free electrons of the nanoparticle, they accumulate at one side of the particle, and the other side of the particle is hole dominant, or deprived of the electrons, less electrons. So they generate electric field inside the particle, which is opposite to the electric field of the electromagnetic radiation, which is falling off the particle. Now the direction of electric field is also changing. So if direction of electric field is changing, obviously direction of the electric field which is being generated inside the particle due to interaction of electromagnetic radiation, that is also changing. And this creates a field, electric field on its own. It creates a dipole actually, right? This is the dipole. So this dipole is creating an electric field, and the way it interacts with electromagnetic radiation now is different than that of the bulk, and that is why the color is no more the same color which we observe in case of bulk nanomaterial, because the wavelength which now the material will absorb and reflect will be different, will depend on the electromagnetic field which these particles will be generating. So the color will change. This is surface plasmon resonance. Now the quantum size effect. Quantum size effect is something where the size of the particle, as the size of the particle, the band gap, which is a property of semiconducting nanoparticles, not nanoparticles, semiconducting materials. So the band gap changes. So when we go to smaller size, the band gap increases. Now this band gap generally you define in terms of energy, right? So this energy is different. H nu1 is more. So nu1 is greater than nu2 is greater than nu3, like that. And this one is, this band gap is associated with high wavelength of the high wavelength of the light, which will be absorbed by this semiconductor. So now this change of band gap with in comparison to the bigger size particle, this shift towards higher frequency is called blue shift. And you might have seen this figure multiple times because it is quite common, and one reason why I choose this figure is the same, that it's easy to explain things here. So CDSE nanoparticles, when they are of bigger size, 5.5 nanometer, they are red in color, whereas you reduce the size to 2.3 nanometer, it is blue. And so it explains the blue has higher frequency than the red, and so this is called blue shift. So this shifting of the band gap or shifting of the frequency of the light which will be absorbed, or the increase in the band gap. This phenomena is called blue shift, and this phenomena is very, very useful whenever we try to design a catalyst where light absorption is taking place. So we will come to that. Yeah, so this is blue shift, which I already spoke about. As we go to increase the particle size, the band gap is reducing with higher size particle, and for small size particle, the band gap is high. Now, these are the other, whenever we are making nanoparticles, we something which we expect is this is the ideal condition where all the nanoparticles should be of the same size, same shape, chemical composition, morphology, crystal structure should be same. The particles should be monodispersed. So these things are something which we expect from us whenever we are preparing nanoparticle. Why? Because if I want to study mechanical property, for example, then I need the particles or the materials of the same shape, so I can define that yes, this size, this shape of the particle has this much of mechanical strength. So yeah, these are the ideal conditions, but it is difficult to achieve. While synthesizing nanoparticle, we can do it either by top-down approach or bottom-up approach. The top-down is when you take bigger size of the material, you break it into small pieces and go to the nano size, and that is called top-down approach. Whereas bottom-up approach is something where you where we take the material from atomic level or the very smaller level, and then we build a nanomaterial. So when we start from smaller size particle and then go to the bigger size particle, then that is bottom up approach. So in this approach, we assemble the nanoparticles. In bottom up approach, we assemble the nanoparticle. We start from atomic level and then we assemble it in the form using some forces. We assemble it and form the nanoparticle. So quantum dots, and we prepare them from these techniques like chemical reduction techniques, sol gel, hydrothermal, microwave synthesis, all these techniques, they come in the category of bottom up approach, because here we are dealing with very small atomic level particle, and then we build something at we engineer the particle, the material. The next one is top-down approach. Top-down approach is something where you already have a bigger size particle, and we try to go to the smaller and smaller size, and we go to the nano size. So that is top-down approach. Lithography, ball mill, they come into, and they come in the category of top-down approach. Now, both these approaches, they have few pros and cons. So top-down approach, they do like lithography, it needs very high clean room facility and other things. In ball mill, the chances of impurity is high, and then the particle size distribution, controlling the particle size is difficult using ball mill. And so comparatively, sol gel chemical reduction techniques, they are easy to do, but again, controlling size is difficult. But yeah, so you can prepare using any of these techniques and choose the optimized one, or you can optimize it. Now, these are the different techniques which we can use to characterize the nanoparticles. So not just these techniques, not only these techniques, but there are many other techniques also which can be used to characterize the particles. So electron microscopy, there are few types of electron microscopy like scanning electron microscopy, transmission electron microscope, high resolution transmission electron microscope. Now then the STM, AFM, these things, they actually they do not come in electron microscopy, but they help us in seeing the particles. So So the electron microscopy is one such characterization tool which we can use to see the particle. Very, very useful technique. Then X-ray diffraction, we can study the crystal size and crystal structure of the particle, how the atoms in the particle are arranged to form the crystal. Then Raman spectroscopy helps us in identifying the phase and how it is that is catching the light. So FTIR, different functional groups which you can attach to the particle. UV visible spectroscopy, this can help in analyzing the structure, molecular structure of the system which we are developing. Then XPS gives us information, again like elemental information, but it also gives us information about more about what is the oxidation state, oxidation state of the elements which are present, and how this is one atom is forming bond with the other one. So detailed information. Along with this, we can use different other techniques also, like NMR spectroscopy and many things. Actually, it depends on us what we are trying to study. The more when we go in more detail of the information, when we want to know more detailed information of the particle arrangement of the functional groups of the nanoparticle, we can use different tools to do that. So yeah, now coming to the application. So the first is energy application. Energy application, when we see these applications I'm discussing, because nanotechnology has helped us a lot in improving the efficiency of these systems. These systems were known since a long time. Like battery, it's not something which is new. It is existing. It is present in the atmosphere since a long time. But nanotech, with the advancement, with the new advances which are taking place every day, the new techniques we are learning to manipulate, modify, and make new materials, it is helping us in achieving better and better performance of these devices. So supercapacitors, battery, fuel cells, photovoltaics, dye-sensitized solar cells, and hydrogen energy, all these are they come in the category of energy application, and they all help us in improving their performance. And we can we can use different types of different techniques to improve the performance of these materials. So so yeah, talking about the battery system, why is it so important, and why we can go to we can increase the performance so high? Because now we have one dimensional, zero dimensional, two dimensional materials which we can use to fabricate the battery and different systems of any vehicle. And we also, and these materials can be used for with different techniques, like 3D printing, like self-assembly into complex architectures, then spray coating, ink jet printing. We can use these techniques to fabricate or to bring together the nanomaterials and use them. So these techniques, they allow us to design the our devices, to design the devices in such a way that it is more useful. Nanoparticles, they have very good interesting property, but what if, but we cannot even touch those nanoparticles, we cannot even see them. So you need to fabricate them, keeping the properties intact, fabricate them in such a way which is usable for us. So this is where these techniques come into picture, right? So where we use the techniques and put the nanoparticles together, retaining their property, and make it in a useful form for us. So talking about the battery system, if we talk about the battery system, India is looking forward for electric vehicles. We do have few in the market, and Tesla is making a lot of news for their lithium-ion based vehicle. And then along with that, Ford Mustang, there are many other vehicles which are there in the market, which which are really giving good performance. And most of these electric vehicles, they depend on lithium ion batteries. So lithium ion batteries, if we talk about these batteries, there are many different types of batteries, like different types of metal ion batteries, then nickel metal hydride batteries, lead acid batteries. And so if we look around, we have n number of devices nowadays which is working on the batteries. So and among these batteries, lithium is something which has very high electrochemical potential. So it is something which can readily donate the electron and convert into lithium ion cation. So this property of lithium makes it special, and this is something which is used in lithium ion battery compared to other battery systems. There are a number of other battery systems, but why lithium is so attractive, and why lithium ion battery in last I think 1 decade it has become so important, and it has replaced many of the, it is being used in all the portable applications, then handheld devices. It is replacing all the other battery systems because of this special property of lithium. But then lithium is highly unstable also. Unstable in the sense it is very reactive in presence of air, in presence of water. It is highly reactive. So lithium is something which can be used for storing the energy, but we need to be very, very careful while using lithium. So very careful we need to have the good control system, safety measures whenever we are using these lithium ion devices. So lithium ion storage or lithium ion battery. So here you have basically on one side of the electrode, you have lithium in some oxide form, which is more stable than pure lithium in atomic form. And then on the other side, we have carbon material, mostly in the form of graphite. So what happens? It is charged when the lithium ions from the oxide, they go and sit in the graphite electrode. So the graphite, we know that it has a layered structure. So if graphite has the layered structure, then these ions, then lithium ions, they go and sit in these structures, and this is called charging. And these electrolyte, basically electrolyte only allows the lithium ion to pass through, but does not allow the electrons. So electrons follow the external path to path, and that is why where we collect those electrons and we use that electricity. So so now this is how the common lithium ion battery works. But where nanotechnology plays an important role is what is the whenever we are designing a battery, what is important? It is important that the more and more lithium ions can be stored in the electrode system. So we need to have electrodes which are we need to have material which can have the property like improved ionic transport and electronic conductivity compared to these battery and supercapacitor materials. So ionic transport and electrical conductivity should be very high. It should have very high surface area where all the intercalation sites should be available for ions to be stored. Am I not audible? Is my voice clear?
Very clear, very clear. Please continue.
Thank you, because some of the comments I'm able to see which says that my voice is low or no sound. So thank you.
No, it's okay.
Thank you. So these nanostructured materials, especially nano architectured electrodes, are very important, because here we can design the electrode in such a way that more ions can be stored, more and plus the electrolyte designing is equally, actually in lithium ion battery or in any of the devices, all the components of the device are important, very important. You need to have it functional, And you also need to make sure that all those it should not be detrimental to the device. So it is very important that you design the materials, electrodes, using the material. You design the electrode in such a way that it is having high conductivity, ionic transport is not hampered, so the diffusion resistance is less. Conductivity should be high of the conductivity of the material should be high, and the electrolyte should be designed in such a way that it allows only lithium ion. Now, another problem which these battery systems are facing, if due to increase in heat, it dries, if the electrolyte dries, then short circuit takes place, right? Because anode cathode comes together. That should not happen, because that leads to fire and accidents. And that was one of the reasons why Samsung had to withdraw its Galaxy Note 7, because of these accidents which was taking place in lithium ion batteries they were using. So yes, we need to be very careful while designing these things. So some of the limitations which nanomaterials in energy storage devices are, because of their very high surface area, some parasitic reactions are also possible. So we need to solve these problems which are hampering the activity of fuel cell. So we need to control the geometry, make the architecture in such a way that we use it in a better way. So we can use all these different types of materials like zero-dimensional carbon onion nanoparticles, quantum dots, one-dimensional single and multiple wall carbon nanotubes, nanowires, graphene, then 2D structures, nanoflakes, then three-dimensional pillared graphene. Nowadays many people are making graphene in sponge-like structure, graphene aerogels, metal organic framework. So we can use all these different materials as electrode system for any of these energy devices, not just lithium ion battery, but all these different types of material. They do have some advantages, but they are also, they do have some limitations also. For example, 3D morphology, when we create, it creates, the good point is we can use that to make thick electrode. Thick electrode means we can store more charge into that. But, so they will have very large areal and volumetric storage property. But then something like MOF structures, they have the stability issues. You need the material, the designing should be very proper, that it maintains the porosity, but and it is equally stable also for large number of cycles of charging and discharging. It needs to be stable. So two-dimensional material, they have very high surface area. The whole material, the whole plane of the material is available for charging and discharging. It can store large amount of charge in between the interlayers. But then the issue is restacking of these planes. So we need to do something where the restacking issue can be solved. So all and these materials, they do come with high cost. So develop a technique which can reduce the cost. Then one-dimensional material, they again have one-dimensional, zero-dimensional material. They have all these advantages and limitations also. So we need to overcome those limitations where we use these materials, but architecture our electrode design in such a way that it is useful. So yes, as I said, safety of the battery is very important. And this lithium ion, because of very high reactivity in presence of both air as well as water, it can catch fire. So the nanotechnology comes into rescue, where you can design the electrode, both the electrolyte, solid state electrolyte are coming into picture, where the chances of that to dry is very less. So there will not be any short circuit between anode and cathode. And then obviously designing different electrode materials with different architectures, different morphology, different properties, which can increase the storage efficiency of the batteries. The next device, which is again very important, is supercapacitors. Supercapacitors, they are used, are actually complementary system to the batteries. Here they can they are useful in regenerative braking, flashlights, flash camera. They have very high power density, but high power density and low energy density. So energy density can be improved by designing the electrode and electrolyte. When this is very good device. If we can improve the energy density, then it can complement the battery system. Where in regenerative braking, so regenerative braking is something, just imagine that we are riding a cycle, and at the signal we apply brake. As soon as we apply brake, the kinetic energy which was there in the cycle because we were riding it, that gets wasted in the form of heat energy. Suddenly you apply brake, and if you touch the area near the brake, it is hot. So what we can do is, so that the same thing happens in car also. So imagine that you are driving a car, you stop at the signal. All this energy, if we can store in something like supercapacitor, which gives high energy for in a very short interval of time. So you store that energy in supercapacitor. As soon as the signal turns green, and this supercapacitor releases energy and it accelerates the car, and after it has accelerated the car, the car can go to some distance. After that, the battery system or fuel cell system, whatever is the main system on which the car is working, that will overtake the job and the car will continue running. So that kind of thing is actually, these devices are there in the market. In hybrid cars it is there. And so the supercapacitors are something which is very important. What happens in supercapacitor? Basically, in capacitors, we have done a lot of study earlier, and we know that this is the equation for capacitor. Now, this is permittivity, area, and distance. Distance between positive and negative. The normal supercapacitor, it has we have these two parallel plate supercapacitor. We have one positive ion, we have electrode, one negative, and they are separated by a dielectric medium. And epsilon is permittivity of that medium. So the basic aim here, when I'm going from capacitor to supercapacitor, my basic aim is to increase the capacitance, to increase the charge storage. What I can do is increase the area multiple times and reduce the D. That can be done using nanoparticle. Now, what nanomaterial is doing, we know that nanomaterial has very high surface area. So that is why when I was discussing about the properties, multiple times I said that surface area is very important. High surface area. And now, if this is one single plate, whatever is the surface area, you can choose it like 1 centimeter to 1 centimeter square. Now, if instead of that plate, similar area, I put something like this, and then then give this potential negative. Store a positive charge here, positive charge. This one is positive charge. So now the D is very less. D is like in the range of ionic diameter, right? D is very less. And area, this area is much more than the area of a plain plate. So that way I'm increasing the charge storage of a supercapacitor. This is what these pictures are showing. So this is discharge state, where you have these electrolyte ions in the center, not on between the electrodes. And then these electrolyte ions, they go inside the, so if they just get absorbed on the surface, and surface is plain surface, then the charge storage is less. But if you have surface like this is the electrode material, positive, and these negative ions. Now, area is very high, and D is very low. D is positive, negative, D actually is very low. And this helps in improving the charge storage many times. Of course, these are like one capacitor here and another capacitor actually here. So they are connected in series. Overall, it goes down, but still it is much higher than the basic capacitor. So now, how do we make these electrode materials? These electrode materials are something which is which has very high surface area. So it increases the overall surface area. It needs to be stable, of course. That is one property. It should be conducting, because you are applying the potential difference. It should not happen that they get charged the transfer of charge should be quick. So it should be conducting, high surface area, and porous. So the porous, why? Because the electrolyte ions which we are having here, it needs to transfer and absorb somewhere in the pores. So the pore size should be optimum. And yeah, if we can make designs of electrode in such a way that you can increase the electrolyte ions, they can come and percolate inside the pores, and when you discharge it, it automatically goes back. So there is less diffusion limitation. So this type of electrodes can be manufactured, can be fabricated using the nanotechnology. So this nanotechnology is helping in making the devices which were not at all we could never think about it in 2 decades ago. So most of the electrolytic capacitors, if you remember in labs in school, we used this picofarad and microfarad maximum. But now these supercapacitors, they have 100 to 200 farads per gram. That is the charge storage. In fact, not just 200. This I'm talking about EDLC, if we say. So they have different types, which I'm not going into detail. But you can go up to 3,000 farads also. So the capacitance has gone up multiple times, and now the energy density is also reaching very close to that of the lithium ion battery and nickel metal hydride lead acid. So this is coming very close to that of the battery systems, and it is much safer than the batteries, because in supercapacitors you do not use any lithium or these metallic systems. You are not using. You can use metal oxide or some polymers to increase the charge efficiency, but then the choice is in your hand. But we are trying to increase the performance of supercapacitor using different electrolytes which are more stable for large potential windows, and we are trying to increase the energy density of these supercapacitors. So I don't know, I think there is some problem, but this is a video, and now at the present day supercapacitor, this is the size of the supercapacitor, which is like 1 rupee coin, and it can lit an LED of 3.5 volts. So these things are possible. I'm sorry, this video and I was expecting that to work, but it's not working. So, but yeah, the supercapacitor can be of very small size and which can have high energy density and power density. Now the next application is fuel cell application. Now again, fuel cell is present with us since 18th century, but the performance was low. How the overall fuel cell works is shown here. You have anode, you have cathode. At anode, you have hydrogen. Hydrogen comes in contact with the catalyst layer. It gets converted into proton and electron. Protons are the green colored ones. They are coming to cathode, and the electrons follow the external path where we can use it. At cathode, again you have the catalyst, and at cathode, these protons, these electrons combine with this hydrogen, this oxygen, and then generate only air and water vapor. So at anode, the reaction is you have hydrogen, it generates protons and electrons, whereas at cathode you have oxygen which combines with the protons and electrons and it generates water. So it is one of the green techniques of generating electricity, right? You are just generating water, and since the reaction is exothermic, some amount of heat is also being generated. But what are the issues here? This catalyst layer which you see at anode and cathode, both the reactions at anode as well as at cathode, platinum is the catalyst, which is platinum is the best known catalyst for oxygen reduction reaction and for hydrogen oxidation reaction. Hydrogen oxidation reaction is good to handle because they are fast, but this reaction is sluggish in nature. So you need to improve the reaction kinetics of oxygen reduction reaction. How can we do it? We can do it by increasing the content of platinum, but again, platinum is very expensive. So It's not so easy to just increase the content of platinum. We will have to do something. So what has been done is platinum, these are platinum nanoparticles, they are coated on these support, which are mostly highly stable. Either amorphous carbon is actually being used, but they are not very stable. So carbon nanomaterials, carbon nanotubes, graphene, they are being studied. So you have these catalyst support, and we are making platinum nanoparticles of very small size, 2 to 3 nanometer size, and deposit it on a substrate which is stable, and then make the catalyst layer, right? So what happens? What are the advantages of this? First, it avoids platinum agglomeration, right? We do not want a lot of platinum to agglomerate with each other. So platinum agglomeration can be avoided. And that is why you need a catalyst support which is stable, because if the material is not stable, it will dissolve slowly with the time and platinum particles will agglomerate. Secondly, the particle size of platinum is very small, and so the percentage of atoms which are on the surface, that means dispersion is high. Dispersion is high, that means more utilization of the catalyst. So platinum is being utilized more. So that is another advantage. So yeah, this is one area which has reduced the amount of platinum which was being used earlier a lot, and still a lot of research work is going on in this area. But we are able to generate electricity, much higher amount of electricity by using the techniques, the technology being developed over the period of last two decades, and thanks to nanotechnology for that again. Next application which I wanted to discuss is dye-sensitized solar cell. So dye-sensitized solar cell is something which is sensitized solar cell is comparatively new. Photovoltaics is where we use this N-type and P-type semiconductors and depletion region, that is known, but dye-sensitized solar cell is comparatively new. And what we do here is we have obviously two electrodes, counter electrode and this conducting FTO glass as one electrode. And then on this electrode, they are transparent to light, they are conducting in nature, and on this we coat TiO2 layer. On TiO2, you have dye molecules. Now you know that TiO2 is a semiconductor material, so it has a band gap. And then you have dye molecule, it has homolumer. So now the dye molecule, and then you have electrolyte and counter electrode. So when the dye molecule, they absorb solar light, and then the electron jumps from ground state to excited state. This is the electron which we are going to use for our electricity purpose. Now, if we want to use it for electricity purpose, I do not want this electron to go back, right, and recombine with the hole. I do not want that. So how to stop that? So that is the main trick, how to stop that electron from going back to the ground state. So the TiO2 has been designed in such a, now we also know that the band gap of a semiconductor can be changed by changing the size of the particle. So you have to play around in such a way that conduction band of TiO2 is lower to that of the LUMO of dye, and electron can be transferred from LUMO to the conduction band of TiO2. And then the electron transfers to the electrode, and we can transfer the electrode through load or through the devices which we want to run. And then the electron comes to the other side, counter electrode, where the electrolyte undergoes redox reaction, and then it can stabilize the dye molecule. So this is how dye-sensitized solar cell works. Now, instead of this TiO2 coating on FTO glass, if we use a TiO2 nanoparticles, then the performance goes up multiple times, because if TiO2 nanoparticles are there, they have high surface area. High surface area can absorb large large number of dye molecules, and then obviously you can also play around with the band gap of TiO2, and because large number of dye molecules are there, fill factor efficiency of this device obviously goes up. We can also, in fact, it has been tried in literature using a composite of TiO2 with graphene or with CNT, because they have very high electron density and electron affinity. So the electron which gets transferred, they can be transported to these materials, carbon materials, and they have high electrical conductivity. So immediately the electron gets collected by the anode, and we can use those electrons for our application. So yeah, again, this device has gone up from, in efficiency wise, it has gone up from 5% to nearly 17-18% in just few years time, again because of the nano materials, nano fabrication, engineering of nano materials, and that has helped a lot in increasing the efficiency of this solar sensitized, dye sensitized solar cell. Now all these devices which we are talking about, these devices, they are very helpful for the environment also, because when we spoke about fuel cell or battery system, the electric vehicles, these vehicles, if they are not running on these devices, then they are running on diesel and petrol, which is we all know that they release a lot of pollutants, a lot of chemicals which are not good for us. So if we want to get rid of those chemicals, it's better to shift to electric vehicles. And electric vehicles again is the area which is generating which needs energy from the energy from the battery systems or supercapacitors or fuel cells or dye sensitized solar cells for that matter. But I mean, these dye sensitized solar cell, it has not reached to the level where it can still be used. We need a lot of more work to do in this area. Now coming to the applications where direct environmental application is involved. So we can use these materials for contaminant adsorption. So for example, I want to adsorb arsenic from water. Arsenic is a big problem, right, in water purification, in water in many states of our country, mostly like Bengal, Odisha, that side, Bihar. So yeah, so we can use some Fe3O4 coated nanoparticles of high surface area and try to adsorb those contaminants. Then sensing application, it can be used because the nanomaterials, they are very sensitive to the adsorption of particles of very small size, and their resistance and optical properties, all properties changes when something gets adsorbed on them. So it can be used for sensing application. Then photocatalysis. Photocatalysis is again the area where semiconducting particles and band gap comes into picture, and we can use them for different applications like membrane separation. We can fabricate the membranes and try to filter the water and other things. So photocatalysis is area where we are using semiconducting nanoparticles. These semiconducting nanoparticles can be used. We know that it generates excitons. So excitons is like where you have electron hole pair. So electron hole pair is generated. That electron and hole helps in water splitting, dye degradation, all the dyes which are going from textile industries to different types of industries, different colors, it is just being thrown in big water systems, and it affects the aquatic life also. Then do chemical for degrading some chemicals and catalyzing some chemical reactions, CO2 conversion into solar fuel. So all these things are something which we can solve problem in this area also using photocatalysis. So yeah, so it can be used in environmental radiations and solar fuel production. So photocatalysis is area which can help in these things. Now the next area I want to discuss is on interfacial solar steam generation. This is again the area where solar, this is very new area, very recent area, and this is nothing but distillation of water. So whatever water system we have, we can evaporate the water and condense it further. The same thing is happening, but the speed is high. So the speed with which evaporation is taking place and condensation is very high. What comes to our mind is, when we think about evaporation, you just add, you have a water system, you cover that water system with something. What will happen? We assume that the rate of steam generation will be low. So if rate of steam generation is low, then distillation will be reduced, right? Rate of evaporation is low. But with these new materials which are being used, photothermal materials, you can increase the rate of distillation. So if you have a water system, you cover it with a type of material which is floating membrane systems, which can absorb a broad band of light, solar spectra, and then it should be hydrophilic and porous and thermally insulating. Why these things? Because what you are doing is, actually you are trying to focus solar light here. We generate hotspot. We generate hotspot here, and if hotspot is generating, that means whatever water molecules are here, it is being evaporated. Now if water molecules are being evaporated, water molecules will come here only if this is porous. So it should be porous, low thermal conductivity, because otherwise hotspot will not be generated. Whatever heat is accumulated, it will transfer to the other parts of the system. We don't want that. We want hotspot to be generated. So it should be hydrophilic, because we are trying to purify water. So water system, so this water system, what we can do is, this water, you coat it with such membrane, it starts evaporating, and then if it condenses on solar still, and then you can collect this purified water. So this membrane needs to have the property like high solar absorption. So it should be able to absorb the solar radiation in very wide range. So I'll show you this is again actually a video which yeah, so this is a video where here you have the water system, and as soon as we add this film of photothermal material, you can see the vapors coming at very high speed. Now this principle can be used to purify water, and the water can be purified using this, fabricating this type of device which is called solar still. And solar still, you have this impure water. So any type of water, like industrial waste water, sea water, anything we can take. And it started by using the Fresnel lens, but now we can skip this usage of this Fresnel lens. The water, it evaporates, it condenses, and then you have a chamber in the solar still where you can collect the purified water. So that way we can try using different types of water and study the purity of the purified water. Another area where nanotechnology is, it can be used, but it is somehow neglected. I don't know the reason why, but maybe because it is not affecting us directly, affecting human beings directly, but indirectly it is. That is oil spill adsorption. You might have seen in now oil spill adsorption. Yes, it is the area which is not given due importance, but it is not very rare also. Now this oil spill takes place whenever the petroleum products are being transferred from one country to another country. Sometimes the ship, they collide, sometimes there is a leak, so the oil spills on ocean surface. And this ocean surface, they form very thin layer of oil. Yes, time is less, because then it spreads across the ocean, across a very large area at a very high speed, but it does affect the marine ecosystem. And so the images are quite disturbing, you can see here, but nothing much is being done in this area where many things can be done. It is possible to do. So at present, what is being done to collect this oil is we sieve rooms. They are called sieve rooms, where the oil is collected and then they are burnt. So that is again not a solution to the problem, because burning, you are removing pollution from sea and putting it in the atmosphere. So that is obviously not desirable. So the another thing where nano structure or materials have come to the rescue is this area where viscosity of oil is major problem. So what you can do is we can make a sponge using or we can coat graphene on the sponge, and then this graphene, it absorbs the oil from the surface. Now graphene is hydrophobic in nature, so it does not take water into it, but only oil. And then these pores are completely filled with the oil, and later on you can remove this oil and use it. So that is one area. Now the problem which was being faced is the viscosity of oil is very less, so it takes a lot of time in filling up all these pores. That can be reduced by using Joule heating, because thermal conductivity of this graphene is very high, and you can use heat. We know that with heating the viscosity reduces. If viscosity reduces, then the transport increases. If transport increases, we can easily fill these pores with oil. So this is an example where from this paper, if you want to know more detail about it, you can go to this paper, where here graphene is coated on the sponge. And a similar study was done earlier by Roof and his group, where graphene aerogel was prepared. Aerogel is something highly porous structure. See, so all these things are pores. It is very lightweight. It can float on the water surface, and it does absorb all these oils on the pores. And then you can remove these. So this is like hydrophobic, and you can remove these oils later and use it. So this many different types of material or solutions were absorbed in graphene aerogel, and the weight gain was much higher. So chloroform, nitrobenzene, hexane, heptane, octane, decane, kerosene oil, pump oil, soybean oil. So many different oils were studied. So this is another area which needs attention. Work is being done in this area, but somehow it has not come up to the commercial level. So nobody is using it whenever oil spill takes place. Another thing is in textile. We know that this area is again like nano material has gained a lot of popularity in textile industries, and now we have designed different military personnel, firefighter, medical workers. They can use this type of specially designed textile or the garments or the materials. Now these synthesized nanoparticles, they can be incorporated into fibers and textile, and sometimes you can also use electrospinning method to make the fibers with the desired properties. So the properties like good filtration, where you can, so that the sweat can evaporate easily, it is more comfortable, high surface area, lightweight fabric, and all these things can be very easily made. And so the properties which we want is like abrasion resistance. Then the material should be very strong. We can also, the supercapacitor which I was talking about, and the battery systems nowadays, that can be made flexible battery systems or flexible supercapacitor, so that if the fabric is electrically conducting and it is mechanically strong, then we can also fabricate the devices, the supercapacitor and battery devices on the fabrics, and make it in the form of like flexible device, wearable device. So yeah, we can control cooling and warming of the garments, and then different effects can be given, where the cleaning required is less. If it shows this anti-static property, then it can obviously repel these materials like dust, dog hair, lint. So I mean, we can design material of any property we want. it has found a lot of use in medical applications, especially silver nanoparticles. They are used in because of their antibacterial property. They can be they are being used in socks, bandage, and they are available in the market. Military use because lightweight, antibacterial activity, better camouflage, water resistant. In fact, for sportswear, many things are coming up in the market from this textile area. Then obviously order-free fabric, wrinkles, we don't want to see wrinkles on our clothes. Water resistant, so it is almost like stain resistant. Also ultraviolet protective, these TiO2 zinc oxide nanoparticles, they have this they do show this UV absorption, so they can be used to remove ultraviolet radiations from reaching your body. So all these different types of fabrics are coming into picture. These are some commercial materials which I just tried to put in this presentation. So along with this, nano socks with nano silver, it's not nano socks, actually it's a normal socks with nano silver, and which gives odorless and antimicrobial property. And so I think a golf ball and tennis ball also, they have made a layer of this carbon nanofibers inside the layer of this golf ball, so that golf ball as well as the tennis ball, so that the pressure is retained. Then the tennis racket, to increase the strength of those fibers which are being used, nanomaterials are used there. So yeah, all these products, self-cleaning windows, I think Saint Gobain is making self-cleaning windows. Then we can use different types of nanoparticles with antimicrobial, antifungal properties for food wrap, sunscreen. Many cosmetics are coming with this type of particles. And so yes, they are available in the market, and some of them are not nano also. For example, nano car, there is nothing nano in that, but it is still in the market with the name nano. And nano pods for music, for listening to music, that also has nothing nano but the name nano, because it is just small. So something, a term which can be marketed very well. So yeah, thank you for listening to me patiently. And let me go to the questions. Nowadays, okay, yeah. So nowadays, nano zirconium dioxide are, yes, for dye-sensitized solar cell, they are being used instead of TiO2. In dye-sensitized solar cell, TiO2, zinc oxide, all these particles are being tried and tested. Zirconium dioxide is also used for dental purpose. So yes, thank you for this information. Can nanomaterial used in wastewater treatment for nitrogen and phosphorus removal? I think for nitrogen and phosphorus removal, much work needs to be done before I give any statement. So I don't want to comment on that. I think fluorine removal, some work is being going on. But yes, if we can functionalize the nanomaterial which has specific affinity towards nitrogen and towards phosphorus, if we attach that kind of functional groups, then it might help in removal of these things from water. Okay. Yeah, if there are any other questions also, please go ahead from any part of my presentation which I have discussed. My voice is audible, right?
Yes, madam, yes.
Darpanji, you unmute everyone. If someone wants to ask something, let them ask. Now that the lecture is over.
Okay. I'm unmuting all. Please unmute yourself to ask any questions.
No, madam.
Yes.
Madam, you have mentioned that when you are characterizing the nanoparticle, no, you had mentioned all the conventional methods actually.
Yes.
X-ray crystallography, then similarly all those things. But you did not mention about NMR. Is there any drawbacks of NMR for using for the characterization of this nanoparticle in specifically?
I would say no, there is no drawback of using NMR, but NMR, see what kind of information we get from NMR. So carbon NMR, proton NMR, we do get information like what are different types, chemical structure is easy to understand, like how many different if you have a big molecule with 10 carbon atoms, 5 of them are in different atmosphere and another 5 are in different atmosphere, then these informations are easy to gather using NMR. But I think it is not very common because of the fact that NMR, accessing NMR is very difficult, right? I mean, there are it's just that analyzing it takes some time, and NMR is expensive instrument, so not all the institutes also they have it, so accessing them is difficult. Plus maybe people are those who are more into developing drugs or the molecules which are helpful in that kind of drug delivery systems, or from pharma department, they use it more than the people who are into electrodes or dealing with the materials which are either in molecular where more like metal oxides and these things are being used, because yeah, they are more common in that area, I would say.
Okay. Thank you, madam. I have one more question. You had mentioned one of the excellent application of this nano-based approach nanoparticle, where we are removing the oil spills from the oceans and the marine ecosystems.
Yes.
And this, when you are coating this nanoparticle on sponge, and once you are removing that oils from the water, and is it reusable, that sponge? How will you destroy that sponge? Or once you are coating, and how long we can use, and it is reproducible and it is repeatedly can be used?
Yes, actually, if you that's a very good question, because if you go through this paper, Advanced Functional Materials 2012,
Okay.
they have tested it for some 10 cycles, I guess, and they could successfully use it. So just by applying pressure, remove oil from the sponge and then reuse it. So that was successfully done for almost 10 cycles. So I would say that it is useful. We can use it. It's just that maybe making aerogels of very big size, which is stable, maybe that is the issue, or it's just that we need to give little more attention to that area, so that because this oil spill doesn't happen every day, right? But when it happens, the after effect is a lot, and for many long years the whole marine ecosystem is affected. And because it doesn't affect us directly, maybe we are not thinking from that point of view, like battery vehicles, cars, and our energy storage devices. These things are something which is affecting us on daily life, so we are thinking more for them, but this is something which is not paid that much attention. But yes, I think it is stable for a long number. Graphene is very stable material. If graphene oxide, it has more functional groups, so it becomes more reactive. But if it is pure graphene, difficult to make, but very stable, so it can be used for multiple cycles. Yes.
Thank you, madam. Thank you very much. Thanks.
Madam, one question, madam. Hello.
Yes, please.
So you are talking about bulk to nanomaterials. So properties is changing here. And
Sorry?
Hello.
Yeah, please repeat your question.
You are talking about from bulk to nano.
Yes.
So properties is changing.
Yes.
So you are also mentioning that the nanometric size is 1 to 100.
Yes.
1 to 100. You are calling it is a nanomaterial.
Yes.
So from bulk to nano, the surface area has become high and particle size is very low.
Yes.
So if we go further finer, that is, you are supposed to say picometric range.
Okay. Yes.
Is it beneficial for us or not?
Then we are going, I think, very close to the atomic level. See, it is my own opinion. If you go to where do you want to go, what size we are trying to reach, the size where it is useful for us. right? So if we go to the very, very small, you are saying that pico range, the size of an atom is 0.2 to 0.4, approximately 0.5, 0.6 nanometers, right? So we need to be in the range where we can use it. Even in nanomaterial, as we say that it was available, people were not understanding it, and now also we can synthesize n number of nanomaterials of different size. But how do we use it? To use it, we have to again fabricate in a system where it is easy to handle by us, where we can handle it. So if we can make a material of the property which I want, right? I mean, I want, for example, if I want to replace all these wirings which we have in our home, the copper wiring for electricity, if I want to replace that by carbon nanotube, because carbon nanotube is much more conducting than copper. But what is stopping me? The size is small, the property is good, right? Conductivity, the size is small, but that much small size I'm not able to handle to make a single carbon nanotube so long that I can replace it. I'm not able to do that yet. So I think we should go to the size where we can manage it, understand it, and use it.
No, actually, madam, before 60 years back, people they don't have any idea about the nanometric range, the nanometric material. But for the time being, they have adopted and they have applied. So, is there any scope to go further? To the experimental part is there, but will be there or not?
I think experimentally we can definitely do it, because all the techniques which we have available nowadays, they can take us to the level of where we can handle a single atom. So we can go there. It's just that we can go there, we can study the properties. If it is useful, we can use it. If it is not useful, we can discard it.
Oh, okay. Thank you.
Thank you.
Neetu, did you check the questions in the chat box? Have you answered everything?
I think if there are new questions that I did not check earlier questions. Yeah, this question was there. Will it be beneficial if we shift to nano to pico range? How to manage contaminant absorbed nanomaterials even after remediation? Actually, yeah, this question is again very interesting. So if it's true that it is a very big problem. If we disperse nanoparticle and then they absorb the impurities from the water, how do we take care of the nanoparticle itself, nanomaterial itself, right? I think this is that question. So the thing is, yes, it is difficult. So the approach nowadays is to use either magnetic nanoparticles, which are easy to collect. And so, for example, Fe3O4 nanoparticles, they are magnetic in nature and they also absorb arsenic. So if arsenic is absorbed on Fe3O4, you cannot just leave Fe3O4 in water. That will become another contaminant and pollutant in water. So we need to get rid of that Fe3O4. Using the magnetic field, we can collect this Fe3O4. This is one approach. Second approach is if we can use fixed bed technique. So for example, a membrane system or a support system where we have a substrate and these Fe3O4 if they are deposited on that, and then you can completely take that off. That way these problems can be handled. People are looking at it from that point of view also.
Yeah, madam, can we conclude?
Yeah, yes, I think I read all the questions. I think I have answered.
Yeah, I think Dr. Neetu answered all the questions. Thank you, Dr. Neetu, for accepting our invitation. And I was just thinking, like when I was in ICT Mumbai that time, how wonderful it would have been if professor like Neetu would have been there explaining the things to the core. Everything perfectly explained.
Thank you so much.
I request Tanaka to do the summary of this particular session.
Okay.
Tanaka, yeah.
Yes. Thank you, ma'am. I would like to place on record a sincere gratitude to Dr. Neetu, ma'am, for this informative. The session was started emphasizing with the promising technology of future, nanotechnology, and an era based on carbon nanotubes. She will explain the nanomaterials from its basics and discuss the classification of nanomaterials like natural, incidental, and engineering. She will write on the application of nanoparticles in ancient times. We also familiarize the eminent scientists like Dr. Richard Feinman, Dr. Taniguchi, Dr. Eric Drexler, whose contributions led to the evolution in the field of carbon nanoparticles. She detailed about the different properties like structural, thermal, mechanical, chemical, optical, etc., and the reasons behind the property change. We also got an idea on the magic number, cohesive energy, dispersion, lattice constants, and atomic stability like factors, which are also the important properties of the nanoparticles. She elaborated on the synthesis of nanoparticles, which majorly consist of the bottom-up process. The various material characterization techniques like electron microscopy, X-ray diffraction, Raman spectroscopy, etc. were also well explained. She also about the several energy-based applications of nanomaterials, which includes supercapacitors, battery systems, fuel cells, dye-sensitized solar cells, and its performance. She gave a brief idea of the like photocatalysis, interfacial solar steam generation, water purification, oil spill absorption, etc. The session was concluded by explaining the significance of nanomaterials in textiles, which has proved to be immensely valuable for manufacturing of protective garments for military personnel, firefighters, medical workers, and users of nano-based fabrics and its commercial applications. Overall, the session enlightened us with advancements in the sphere of nanomaterials. Once again, thank you, ma'am. Thank you for this good session.
Thanks a lot, and thank you for inviting me to.
Thank you, Tanaka, and thank you, Dr. Neetu. Dr. Neetu, you can log out. Participants, I am giving a 4 minutes break. At 12:05, the next person is logging in. So that time, please come back, stretch your legs, have a cup of coffee or something of that sort, come back with us. So we will be meeting at 12:05. Thank you.